All right, here we're going to take a look at graphing linear inequalities when the inequality is written in slope-intercept form. So a reminder, slope-intercept form is the one that gives us the slope of the line and the y-intercept of the line. The only difference today is that instead of the equal sign, we are going to get one of our inequality symbols, perhaps like this, less than or equal to. So here are the steps that we want to follow when we're graphing a linear inequality in slope-intercept form. We start by graphing the boundary line. The boundary line is basically the same as that equation where we have all of those solutions where the y value will equal the m times the x plus b. So identify the slope and the y-intercept to get your boundary line in place. But before you actually draw the line, there are two different types of lines that we have to look out for. There are solid lines, and we use a solid line if the inequality has the little bar underneath it. Remember that that little bar in the inequality symbol means or equal to. So if either inequality symbol has the or equal to part of it in our linear inequality, we want to graph a solid boundary line, just like a regular line. However, there are also dashed boundary lines that we have to watch out for. A dashed boundary line is used if it's a strict inequality. If it's just less than, or if it's just greater than, we use that dashed line with the example there off to the right. So a solid boundary line means that all of the ordered pairs that are right on the line are parts of the solution set. A dashed boundary line means that the ordered pairs that are right on the line are not part of the solution set, even though both lines represent the boundary, or I guess kind of like the split between one side of the line has all the solutions, the other side has none of the solutions, or all of the non-solutions. So step two then is once we have our boundary line in place, we shade the side that has the solutions. Now, here's the neat thing about slope-intercept form. If you look at the inequality symbol, we can tell what side of the boundary line to shade just by checking if it's a less than symbol or a greater than symbol. So in this case, we see that we we shade above the line, the upper part, if it's one of the greater than symbols. Okay, so if it's a greater than or equal to symbol, we shade above the line. If it's a greater than symbol, we shade above the line. However, we'll shade below the line if it's one of the less than inequality symbols. So less than or equal to, we shade below the line. Less than, we shade below the line. So think of it as the y-axis. Where are the larger numbers? The numbers that are greater, up above. So we would shade above the line for any of the greater than symbols, below the line for any of the less than symbols. So let's take a look here at our first example. We're supposed to graph y is less than 2x minus 4. We know that's a less than symbol because it is pointing to the left. So in this inequality, just like as if it were an equation in slope-intercept form, the slope is the number in front of the x, and the y-intercept is the value at the end. Okay, so we have a slope of 2 and a y-intercept of 4. So we're going to go ahead and get our boundary all set up. So I'm going to start by plotting the y-intercept at -4. I'm going to use my slope. Remember, I can turn that into a fraction by putting a 1 underneath it. I can see my rise over run. Rise 2, run 1. And I want to do this as many times as I can, as many times as I have room for, because I have to split my graph in half, and then I have to shade one side or the other. So here's my boundary line. Now, the one thing I forgot to do before I drew my boundary line is I have to double check and see what type of line we have to draw. And that all goes back to the inequality symbol. My inequality symbol is a less than symbol, not equal to, just less than. So that means I want to draw a dashed line. That's from our notes on the previous screen. Dashed line because it's not the equal to type of inequality. And then for the shading, I want to, let's see, less than on the y-axis is down by the negative number. So I want to shade below this line. So I have to go back. Let me change this line to a dashed line. I think I can do that pretty quickly. There we go. So there's my dashed boundary line. And then for my shading, I'm going to go ahead and you guys can just use like your pencil or a tool to do this. I'm going to use my highlighter and make it as big as possible. And the lower side, when I shade this, so let me just start by drawing a vertical line through that. Think about which side of my boundary line, the dashed line, is below it. In other words, straight down. Well, that's going to be the side over here. I'm going to go ahead and shade this side because that shows all the solutions are on that side of the boundary line. Any ordered pair on that side of the boundary line would represent a solution. So that's how we graph our linear inequality. All right, so for number 2, we have y equals negative 1/2 x plus 3. I see my inequality symbol is greater than or equal to. So that tells me 2 things about my type of line and my shading. Because it's the or equal to this time, that means that any point on the boundary is a solution. So we want to make sure to draw a solid line to represent that. And because it's one of our greater than symbols, we want to eventually shade above the line. All right, so let's see, what's our slope? Our slope appears to be negative 1/2, and our y-intercept appears to be positive 3. So let me get my line in place. I start with my y-intercept of 3. My slope is a negative 1/2, so I make sure I go down 1 and right 2 for my rise over run. And let's see, I can go backwards a few. There we go, up 1 and left 2. And I'm going to draw my line, and let's see, we did say solid line this time. Not like last time where I had to go back and change it. Whoops, let's try that again. Line. That's better. Solid line, mostly going through those points. And we said shade above the line. Grab my highlighter. Let's do yellow this time. And above the line is going to be up here. Any ordered pair above that line. Now keep in mind, this graph actually goes on forever. So there's an infinite number of points. This line, this half plane of shading would go on forever. I could shade forever if I had the space to do it. But just with the part of the graph that we have visible, just that part up above. All right, last one. We have y is greater than negative 2. Now, just like when we worked with equations, where we had just y equals a number, we have to think about what was that number in front of the x that would have given us this y, well, say y equals negative 2 for the sake of just thinking of it as an equation. If x is not in this equation, that means my number in front of x was 0 to make it go away. So my negative 2 is actually my y-intercept this time. And I have a slope of 0. Or since I'm graphing, I'll think of it as 0 over 1. Now for the type of line, I see that I have a strict inequality. It is greater than, but it is not equal to. So I want to go ahead and make a dashed line because it's not equal to. I want to leave it as like a broken line. And then for my shading, let's see, it's a greater than symbol. So on the y-axis, the numbers that are larger or greater are the ones up above. So I'm going to shade above this time. So we have everything in place. It's time to get our boundary line and shade. So I start with my y-intercept of negative 2. And if it has a slope of 0, you might recall that is a flat horizontal line. Or you can plot more points by using that slope 0 over 1. So rise 0, run 1, rise 0, run 1, rise 0, run 1, and so on. We draw a dashed line. Let's see if I can get the straight line here to work. I already have the dash selected. And I'm going to go straight across here. There we go. The last thing we need to do is shade where all of the solutions, where are all the y values that are greater than negative 2? They are going to be above that line because that's where my y values of negative 1, 0, 1, 2, 3, 4, 5, and so on. All of the ordered pairs in that shaded area would represent the solutions to this inequality.